Hello. Our attention is largely focused on the intracavity field inside the laser. Now, what we're interested is the simplest of the laser kind, which is the continuous wave laser. And we are looking at the output of the laser, which is precisely what is our main interest. Clearly, getting the output in an optimal fashion is going to be crucial. Let me just explain that qualitatively. If we have a lot of field inside the cavity, that would mean that the field that the gain within the cavity will get saturated because the field is large, effectively reducing the gain. On the other hand, if you don't have sufficient electromagnetic field within the cavity, that would mean that the stimulated emission process itself would suffer. So to maintain this balance, one has to carefully now think about how does one optimally extract the light which has been generated from the cavity. And to do this, we are going to look at the simplest composition of the laser. And I'm making a series of approximations, all of which are familiar to you, but we need to make this to keep the matters simple and to the point so as to focus on the essential functioning of the laser rather than getting into the details of individual lasers, which can be quite complex. All right, so the first approximation which I am making is I'm looking at a CW, that is a continuous wave output. That would mean that my I out is a constant, okay, and it is not changing in time. The second approximation is that our field, which is oscillating within the cavity, right? Field is in a single mode. We are looking at a particular mode of the field. So we are looking at a single mode oscillation within the cavity. That is my I nu is a narrowband field at a particular frequency within the cavity. The next approximation that we are making is that our system is homogeneously broadened, right? This is to ensure that we have a relationship between the gain and the intensity of the form that we have written down, which is the gain saturation, which is typically true for homogeneously broadened active media. The next approximation is that we will ignore the transverse variation of the field, right? We are looking at the Gaussian beam profile and so on. I am not going to worry about the transverse profile, but indeed that is a matter that we need to worry about and also probably control by using appropriate cavity mirrors, avoiding diffraction and so on. But we are going to ignore at the moment the transverse profile of the field. Not just that, we are also stating that the field is uniform along the cavity. That would mean that my I plus and I minus are comparable, right? This comes from the fact that my reflectivities R1, right, and R2, these are all quite close to 1, right? If they are, then you see that I plus and I minus are not only equivalent, they're also, we are also demanding that they are uniform within the cavity. Now you do know by making this uniform or mean field approximation, what I have ignored is also the spatial hole burning. I have essentially averaged over the spatial variation of the field. So that is another approximation that I am making here. So given all this, uh, we can now start analyzing as to what such a lasing medium would result in. We know that the rate equation that governs the intensity variation of a light within the cavity is di nu over dt. This is simply c times small l by capital L. Remember, we differentiated between the length of the gain medium versus length of the cavity, and g nu times I nu minus the output coupling 1 minus R1 R2 times I nu, right? So you recall this equation that we had obtained earlier. Remember, this is still an approximate equation because we are not looking at the contribution to the intensity from spontaneous emission, for example. right? Spontaneous emission does not contribute to, we are saying, the cavity photons or the lasing mode which we are talking about, because the contribution is far too small to worry about when lasing is the dominant phenomena. This will not be true. For example, if we analyze the rate equations for photon number or photon intensity or the intensity of light within the cavity, this will not be true if we analyze the intensity of the cavity at threshold, for example, where it is the stimulated emission has not taken off yet. The amount of field is very small, and hence the spontaneous emission would have definite contribution at the regime of threshold. And of course, it doesn't play such an important role when the laser is operational. All right. So now that we have the following rate equation, and we want to demand that my output is a constant, right, in time, that would mean that my intracavity field I nu itself is a constant, right? You cannot have a situation where the intracavity field changes in time and yet the output is a constant, right? So once you're given this and I set this di nu over dt, let me call this as equation number one. If I set this di nu over dt to 0, you will get the following, that the gain term, which is governed, which has, of course, a combination of stimulated emission as well as absorption, because it's a difference between the two populations. The gain term and the loss term have to be equal, right? That is the generation of photons and the extraction of photons from the cavity basically balance each other. And if you're away from any this condition, you would not get a time independent constant output intensity, right? So this implies the following, that my C small l L G of nu I nu is equal to C by 2L 1 minus R1 R2 times I nu. So this is an amazing constraint on the gain. And essentially what one is saying is that my G of nu equals to 1 by 2L 1 minus R1 R2, and you will quickly recognize that this quantity on the right is essentially the G threshold, right? So to obtain a CW oscillation or CW output from a laser, the gain needs to be clamped at the threshold value. That is an interesting consequence of simply considering these equations. This is what is called as the gain clamping condition, right? So what is the consequence of this? So all that one is saying is that my G of nu, which is, by the way, G naught of nu, and again I'm introducing the uniform field approximation, which is 1 plus I nu plus I nu minus divided by I nu saturation. This quantity is equal to G threshold. That is the gain clamping condition. And now let's quickly rearrange and see what we get. So what we get is I plus I minus, right? This quantity is simply equal to, you can do it for yourself and do a little bit of algebra and convince yourself that this is I nu saturation times G naught of nu by G threshold. All that I have done is to uh, take my G threshold on the left hand side and take this denominator to the right and rearranged it. So what I get is G naught by G threshold minus 1 times I nu saturation, right? What this means is that I have a, a cavity, and I have this field that is bouncing back and forth, I plus and I nu. And imagine that my one mirror is completely reflective, that R1 is 1, but my R2 or R is the output mirror, and that is finite. So that is where my I output comes. So what I have effectively stated is that my I nu out is simply the transmission of this right mirror number 2. It's simply T times the I plus, right? So the right propagating field is the one which partially comes out as a output. So this output is my I out, and the one which was propagating that way was I plus, and the one which was propagating backwards was I minus, right? So this is my increasing Z direction. All right. So now that we have fixed this, so I also have assumed that my reflectivities, they might be finite, but they are still quite close to 1. One can have 0.96, reflectivity, 0.98, and such kind of high reflectivity mirrors are what are used for feedback. So I know also that my I plus in magnitude is comparable to I minus, right? This is not true if the reflectivities were as small as, let's say, 20% or 30%. That would be these two quantities would be significantly different, because you see large fraction of the I plus would not be reflected but would be taken out if the reflectivities are close to let's say 20 or 30%, right? Because the reflectivity is close to 1, I plus and I minus is more or less comparable. So given that, I can write down my left hand side of this equation. I can replace it by a factor of 2. So you see, I can rewrite my I out as the following. My I nu out is simply, so this is so this quantity on the right is simply twice as much, right? So I can write this as T times half times the right hand side, which is I nu saturation, the small signal gain divided by the threshold gain minus 1. Please be very careful. What we have clamped is the gain, right? The gain clamping condition needs to be carefully understood. What we have clamped is the total gain and not the small signal gain, right? So gain, the total gain has been clamped to a value of G threshold, and that we have to distinguish from the small signal gain being clamped. Right. So now let's open this up a little bit and do a little bit of algebra to get more insight. I know that my G threshold is simply 1 by 2L. Now in our case, the one mirror was completely reflective, R1 was 1, so I can just write this as 1 minus R. Now I do know that at my second mirror, I do have the relationship, if you recall, that R plus T plus any scattering loss at that mirror is equal to 1. So I'm saying everything is happening, all the action is happening at the output mirror. So I can as well write this as 1 by 2L, and 1 minus R can be replaced as T plus S. So you see, my I nu out, if I put this back into my output intensity, it is simply half times T I nu saturation. It is twice G naught nu small l by T plus S minus 1, right? This, I'm calling this as equation number, so let me call the gain clamping condition as equation number 2, and this equation as equation number 3, right? So you see, I have got now my output intensity, and the following is true. That is, if I choose my lasing medium, that would mean that I have chosen essentially my system. So my I nu saturation gets chosen. My pumping mechanism, for example, is also chosen, the lasing system. So my G naught of nu gets fixed. My level scheme is fixed and the length of my gain cavity is fixed. So given all this, one is asking now what should be the transmission of the mirror, of the output mirror to obtain optimal gain, optimal output. Again, as I told you, physically, this is quite apparent because if I retain too much intensity within the cavity, my gain gets saturated. If I don't, student emission is not good enough. So see what I need to do to maximize my output. I need to obtain the maximum out of the laser. I need to carefully choose my transmission coefficient, right? To obtain the maximum, right? So what I do is to calculate, that is, I use the condition that my di nu out over dt now. Remember, t is not time here, t is the transmission of the mirror. Imagine it's a parameter that you could continuously vary and look at the optimal value. So hence I am doing this and I set this equal to 0. And then I would request you to please do this exercise at home and you will get the following value for the t optimal. Once you set it to 0, you take t on one side and you see that the value of t optimal should be the following. It is twice G naught nu L times S minus S. This is a important result and this I'm calling it as number 4. So once I get my T optimal, I plug this T optimal back into my equation number 3. That would result in the I nu out max, right? The maximum value of the output. And that, by the way, is simply I nu saturation square root of G naught nu times small l minus square root of S by 2. S, by the way, is a scattering loss and the whole square. So this is our main result telling us that if I choose the optimal value of the transmission coefficient, this is the a maximum intensity that I can extract from my laser, right? And clearly, larger the I nu saturation, greater is the intensity that you can extract. So even though we considered I nu saturation as some sort of a scale at which gain gets reduced, but larger the value of I nu saturation, that larger the intensity that the cavity can support without getting saturated is good for the amount of output that you can extract is proportional to I nu saturation. Not just that, the larger the small signal gain, greater is going to be your output. Larger the length of the cavity, you're going to do better. And you need to reduce as much as possible the scattering losses into modes which are not the lasing modes or absorption of the mirror. What you want to do to get the maximum out, you want to choose conditions such a way that my G naught of L uh, or rather G naught is much greater than S by 2L, right? So you want to basically make sure that this is indeed true. And if you choose it to be that, then you see that my I nu out max, if we can manage that, reduce the scattering. So engineering of the laser has to be carefully done with immense care to losses that should be avoided and kept at a minimal when it comes to choice of material, the engineering of the mirrors and so on and so forth. And the maximum possible output you can get is essentially I nu saturation times the small signal gain times the length of the cavity, right? That's the best you can get out of these systems. So this is a very, very important result. I would like you to derive, equation number 4, equation number 5 from this equation number 3 and convince yourself that this is indeed the case. So one can literally think of G naught of nu as that parameter that allows you to extract the maximum out of the laser. Okay, and the the larger the value of G naught of nu, you have essentially offset the role of G threshold, because G threshold is the measure of loss. And smaller the G threshold, greater the G naught of nu, the larger you can extract out of such a system. And there is a notion of an optimal transmission of the mirror. So let me just show you the. So now we are looking at graphically how well one can, as a function of the transmission coefficient, one is asking how does the output look like. And these have been plotted for certain parameters, but it's reasonably universal. So on the right hand side, uh, along the x-axis, I'm looking at, for example, transmission, right, in percentage. So for example, let me give you some exact values. Let's say this 6%, 12%, 18%. Um, and then one is looking at uh, what I'm plotting is I out divided by I new saturation, right? That quantity. And typically, my maximum could be about 0.04, 0.03, and so on. So what I get is a curve of something of this kind. And imagine you also have spatial hole burning switched on, then you see what happens is that the gain actually decreases. So clearly you can see that there is an optimal value for the choice of the transmission coefficient, right, which gives you the maximum output. So this optimal gain has been obtained experimentally, and I will show you the experimental setup that allows us to do that. Essentially, what one is measuring experimentally is equation number 3. So one has fixed the gain medium. One intends to vary the transmission coefficient of the mirror, which practically cannot be done. So what is the underlying technique one uses to get to the optimal transmission coefficient? So again, what we are capturing is equation 3 experimentally. All right, so this is the setup, and so let me just give it a title here. What we are looking at is actually measuring two things. We are going to measure the small signal gain, that is my G naught of nu. And the second thing we are going to measure is basically the optimal output coupling, right? That we will do next. So first just look at what we have. So what I have here is the laser cavity, right? This is my mirror 1. This is the mirror 2. This indeed is the output coupling mirror. And this is the gain medium, right? The gain cell. So what one is doing here is within the cavity, right? One is introducing a knife edge. This is a knife edge. And this knife edge is riding maybe on a micrometer screw. So as you turn the screw, you basically introduce this knife edge within the cavity. And clearly this introduction, it blocks the mirror from the feedback that is going around. So you will see that the part of the feedback is being taken out of the cavity because of this mirror riding essentially on a knife edge. So this output, it no longer participates, right? This output which is going towards my detector no longer participates with the feedback required to sustain the gain in this gain cell, right? So this essentially is the field going back and forth. So right, and what we have done is taken partially that field out into my detector. So imagine that this power which is measured by this detector, let me call it as P scattered, uh, because of the fraction of the intracavity intensity that has been occluded by the knife edge. So I can get a new sort of a scattering coefficient S, right? Because now I am taking light which was in the lasing mode and putting it out. I can call this as simply PS divided by P plus, right? Where this is the power S is the measured power at the detector, and P plus is the uh, power which is traveling to the right. For example, here in this case, there's an output mirror. So the output mirror has got a transmission T. So I can relate my P plus to the P out. So for example, P out uh, is simply the transmission which I know of the mirror times P plus, right? So if I reverse this condition, I will get essentially P plus. From there, I can get my scattering coefficient. So what is going to happen is the following. So we know that the lasing is going to occur when the gain is going to be such that it is larger than gain threshold, right? So when my small signal gain is larger than gain threshold, you will see that the lasing will happen. But you see that as we increase the fraction of light which is scattered off from the feedback, you see at some point the this lasing is going to shut off. So it is when the losses overcome the amount of gain in the system that you would see that the laser is shutting off. And essentially that point where just prior to this, you're going to see that the feedback is going to be minimal, and hence that gain corresponds to the small signal gain. And because we know now G threshold, we know that it is simply 1 over 2L times, or it is simply T plus S. The T is known. We might distinguish between a intrinsic S, which might be there in the system without the knife edge, plus you have introduced another S, which is arising from the knife edge. So this threshold, this is measurable because I can measure individually all these quantities, and this value B is how one actually measures the G naught of nu, right? So this is that's why this is called the maximal loss method to measure the small signal gain, right? So I hope the point is clear. Let me quickly repeat it. What I have done is I have got a laser that is operational, and I introduce a knife edge within the cavity that takes away part of the feedback. As I keep taking larger and larger fractions of the feedback out of the laser, then you see that the losses in the system are increasing. These are essentially what I'm calling it as the scattering loss, which is given by the measured power by the output which was there at that point in time, right? So that gives me the scattered power out, or the new scattering coefficient which I have introduced. And this scattering coefficient is precisely used to get my threshold at which the lasing ceases, because as I keep introducing the knife edge, the lasing eventually at some point would cease because the feedback is becoming smaller and smaller, and that particular value of the G threshold obtained then is exactly equal to the small signal gain, because small signal gain is the situation wherein one is just overcoming the losses for the lasing to take place. So any reduction in this scattering loss is actually going to lead to now gain. It is that point wherein we have sort of experimentally measured the small signal gain. A small variant of this method is also used to determine what is the optimal coupling, T optimal. So I'm now looking at a technique to obtain optimal transmission, right? And to do this, um, we are using exactly the same technique, but with a slight variation. All that I'm doing here is, this is my mirror 1, this is my mirror 2, which by the way is the output coupling mirror. Again, what I've introduced here is the knife edge. And in this variant, what I am doing is I'm going to take not only the measure the power that is scattered from within the cavity, the output also is measured and put back into the same detector. So this detector is simultaneously measuring both the input as well as the output power. So, so my goal is to find out T optimal, right? That is precisely what I'm looking. And what I have done here is for my output mirror, I have chosen a T which happens to be less than the T optimal, right? Because I cannot vary my transmission coefficient continuously. So I have chosen my T at the moment, which is less than the T optimal. So what is happening now is the following. Obviously, because I have chosen my transmission coefficient lower, that would mean that my intra-cavity field is larger. That is, I am in a sense saturating. Such a choice is leading to greater feedback within the cavity. That would mean larger intra-cavity field, and hence my gain is actually effectively getting saturated for a certain amount of pumping, right? So that I am not varying. So as I introduce my knife edge, I essentially measure the two things. I measure the P in, right? I can block the output one and measure the P in. Similarly, I can measure the P out, and hence I can also measure P total. This is my total radiation, which is simply P in, the power from within the cavity, plus uh, P out, power which is coming from the output mirror. Now you see, what I do is keep varying the knife edge which is riding on a micrometer screw until I obtain the maximum value for P total, right? What would that mean? It would mean that there was a certain amount of feedback. The feedback was excess because I had chosen T to be less than T optimal. And because I have now taken away part of that feedback out and put it as an output. So this P in is like an output which should have come out of the output mirror that has been taken to the detector. The moment I maximize this total intensity, right, I have obtained my essentially my T optimal. So I can write that mathematically in the following fashion, that my S, which I have introduced because of the knife edge, is simply P in by P plus. But I do know that my P plus is P out by T. So my S scattering loss at the point where the output is maximum is simply P in by P out times T. And the situation when I maximize my measured power in the detector, maximize detector power, which is clearly the output as well as P in plus P out, that is the total power. Once I maximize that, I'm calling that S as S optimal, right? So what I have done is the following, that my T optimal now becomes the T I have chosen for the mirror, which was less than the T optimal plus S optimal. So this is the new design of the mirror I need to obtain to get optimal output from such a laser. So clearly you see that the experimentalists have come up with a very clever way of measuring all these quantities like the small signal gain, the optimal transmission. Let me just point out a small thing. So imagine if my laser system was a gas. In that case, you see that one can essentially ignore the effects related to spatial hole burning, because you see that the gas atoms do not stay in one place. They actually, because of the atomic motion, they actually move all over the gas cell, and that kind of averages out the effects of spatial hole burning. But for example, if one had a solid state laser, if one would like to remove the effects of spatial hole burning, then one can use something called a ring cavity, right? Which could be a unidirectional the cavity of the following form, uh, where what I have is now not just two mirrors, but a combination of three or four mirrors, wherein this becomes my output mirror, and the light in my cavity is moving in a unidirectional fashion, and this is my output. So such a cavity wherein the gain medium is in one of the arms is actually going to have a traveling wave kind of a field within the gain medium. Hence, this will overcome the notions of spatial hole burning. All right. So in all this discussion, we have focused our attention on homogeneously broadened media. Now, when it comes to inhomogeneously broadened media, the story is extremely complex, and it becomes even more complex when we look at saturation in the homogeneously broadened media. And hence, I will just talk about the Doppler broadening and which is the inhomogeneous broadening mechanism, and the effects of saturation on Doppler broadening in the next lecture.